So having refreshed the concepts of integrals in one dimension, let's move on finally to see a double integration, which is an integral in 2 dimensions. So let's first focus on this graph here. Okay, so this is an integral in 1 dimension. So basically what we are saying is you define a certain interval along the x variable, which is a 1-dimensional variable, right? So we define an interval there, and we simply calculate the area under a certain function. And this is a single integral. Well, a double integral is the same thing, except that instead of having x, we have x and y. And therefore, instead of defining an interval in 1 dimension, we define an area in 2 dimensions. So this is how it looks like. The double integral, which we write by writing 2 integral signs of a function f of x, y. So now the function has 2 variables, x and y. With respect to dA, can be interpreted as follows. This is function f of x, y, which depends on 2 variables. So I need to draw a 3-dimensional diagram now. Okay? Now you know that a function f of x, y is, now you can imagine it as a surface, right, in 3 dimensions. But first, let's define the area of integration. So in 1 dimension, you just have to say between a and b, and that defines a certain line, right? So this time, what you do is that you define a certain area on the xy plane, okay? So this area might be a rectangle, and in fact, to start with, we will always consider rectangles, but this is area A, yeah? And this is the A that you write here to denote the limits. So you don't write limits explicitly, you just say double integral on the area A. And then instead of saying dx, we are now saying dA, which is the differential of this area A. So now what you have to imagine is that the function f is defined on top. So remember function f. Let me enlarge the y-axis so that I have space. So the function f is just a surface in 3 dimensions, right? So maybe it looks something like this. So it's a surface in 3 dimensions, which we can calculate over this area A. So this is the function. So now instead of calculating the area under the curve, now we are calculating the volume that is under this surface, okay? So this will be this volume V. So that is how you can interpret a double integration. It's as simple as that. So this block here, this volume here is V, which is the result of this double integration, okay? Now, let's look at the definition. So in an analogous way to how we defined the integral using the Riemann sum, which is basically dividing the interval into sections and then creating rectangles and then adding the area of those rectangles. So now we are going to do exactly the same, but in this 2-dimensional case. And for that I have an applet that I can show you. So imagine here you have the area, which is this, in this case I chose a square area on the xy plane, okay? So the xy plane is the horizontal plane here on the bottom. So now what I did is I divided this area into squares, okay? And each of these squares is equivalent to the delta x that we had in 1 dimensions, but now we have this square, which is like a delta A. It's a certain subdivision of the area into these tiny squares. And then for each square, we find the value of the function at some point inside the square. In this case, I chose the simplest possible point inside the square, which is just the center of the square. So at the center of the square, I evaluate f of x, y, and this gives me this height here. Yeah, remember the function f of x, y is a surface where the height of the surface represents the value of that function. And x and y are the axes here along the bottom, yeah? So now what we do is, similarly to how in the one-dimensional case we divided the region into these intervals, and then we did rectangles here. So now in 3 dimensions we are going to do something similar, and let me activate it. This is what we do. So we evaluate the function in the center of each of these squares, and we create this cuboid, okay, which has a height equal to the value of the function at that point, and the area of this cross section is just dA or delta A. Okay, so we do that for every point within that grid that we created. And now we do the limit when these squares tend to 0. So as we do the limit, we're getting closer and closer and closer to the actual smooth function, the original smooth function, right? And now, every year that I see this, it reminds me of Minecraft, right? I hope I'm not alone here, but this looks like a mountain in Minecraft. So now what is clear is that if we sum the volume of these cuboids, in the limit when the little squares go to 0, the volume will be equal to the volume under the smooth curve, the original smooth curve. Okay, so let's write that down. Let's use a similar notation as we did here for 1 dimension, but let's do it in 2 dimensions. This will be called the Riemann sum, and it's a way in which we will define the integration as a limit. So the double integral on an area A of a function f xy with respect to area A is equal to a Riemann sum. So how are we going to write it? So let's consider, in general, here we have our xy plane. So let's consider the most general case of an area that has some arbitrary potato shape. Okay, so this is now our area A. So how can we divide it into little squares? Well, we can choose any division we want, but let's say we choose a rectangular grid, something like this. And let's say we only choose those squares that are most of the square is inside of the area, and we ignore those squares that are mostly outside of the area. Okay, so we would count these squares. So then we can number them: 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay, so then what we have to do is we have to do the limit when this area delta A goes to 0, and remember that delta A is the area of each of these squares. The limit when that area goes to 0 of the sum when I goes from 1 to n of f evaluated at each point. And what are the points of evaluation of f? So remember, for each small area we need to evaluate the function at a point. Okay, so those points we can call them xi and yi. Okay, so it depends on which square we are. So this is f evaluated at xi yi times delta A, because we are doing the height of the cuboid multiplied by the area of the little square. And therefore we are getting these cuboids that we are adding up as you had seen earlier. Yeah? So this would be delta A, the area of this little square, and the height of the cuboid is given by the function evaluated at that point. So that's one way of writing it as a single sum. And this is a very, very general way of writing it. But many times, or in most cases, let me remove all of this, the area happens to be a rectangle. So let me draw a rectangle. So imagine that this is our area now. Okay, that's similar to what I drew here as an example, and is similar to the examples I was doing in the applet. Yeah, so the area is a rectangle, and this rectangle has limits AB in x and CD in y. So let's write those limits. So we have AB in x and CD in y. And then this means that we can find an easy way of dividing this rectangle into small into small rectangles, right? And that's just doing like this. Let's assume I did them of equal size, okay? So now each of these is an area delta A, which will be equal to delta x times delta y, okay? Where delta x is the step in the x direction and delta y is the step in the y direction, okay? And now we can number these rectangles. So now we could have a variable I which goes through 1, 2, 3, 4, 5 in the x direction, and then a variable j that goes from 1, 2, 3, 4, 5, okay? So that each of these rectangles is identified by a certain I and a certain j. For example, this one would be ij equals 3, 3, okay? And then this means that we can write this integral as a double sum, right? Because we can have a sum along I inside a sum along j. So we can write the integral as the limit when delta x goes to 0 and delta y goes to 0 of this double sum along I and along j of the function evaluated at the center point. So this time I have to write xi and yj times delta x times delta y. And this is the definition as a Riemann sum of a double integral defined on a rectangular area A, okay? And this is how we are going to start doing integrals at the beginning. So just as a little spoiler, notice that this, comparing this definition to this definition, you might notice that it's just one integral, which is this parenthesis here, inside another integral, which is this parenthesis here. So indeed, double integrals are an integral inside of an integral. And indeed, this means that we can write this double integral using explicitly the limits along x and along y, okay? And the way we would write it is, we still keep the two integral symbols and the integrand is the same, but then we can write dA, the differential of area, we can explicitly write it as dx times dy, okay? Because the same way that delta A changed into delta x times delta y, in the limit when they go to 0, they become the differentials. So now it's dA and it's dx and dy, okay? So it's the same thing, dA is equal to dx times dy. And now the good thing is that this explicitly is telling us that we have to do two integrals, one on x and one on y. So the first integral on x will have limits from a to b, which are the limits along the x direction. So we can write a to b, while the integral along dy will have the limits corresponding to y, which are c to d. So therefore, we can write the limits here, c to d. Okay, so this is an alternative way of writing a double integral on a rectangular region. Okay, so just to recap, this is the general way to write a double integral on any area A, which might be a blob, it doesn't have to be a rectangle, and then we use dA in the most general case. Or if we write it in a rectangular area and using x and y as our integration variables, we write it like this. So we write specifically the limits for each of the integral signs. Okay? So thank you very much for watching and see you in the next video.